Hi, my name is Nicholas Wiley, and this is Material and Energy Balance, Homework 3, Part 1. Now, the first thing we're going to do is we're going to read this problem statement, and to show there is no cheating, that is just the problem statement. So, I'm going to read it to you. 3 tanks with specific cross-sectional areas are interconnected at their bottoms with specific initial fluid heights per tank. The magnitude of flow between each tank is proportional to the square root of the difference between the 2 interconnected tank heights. We will use flow proportionality constants to determine flow between these 2 tanks. Tank 3 is a set point we will try to reach, a set height we're going to try to reach and have the steady state value revolve around that. And tank 2 has flow going into it using a proportionality constant in unison with tank 3's height and set height. So let's get right into this. Now the best thing to do, at least for me as an engineer, is I like to diagram things out. This will help us figure out where we need to go. Now I keep trying to get these to be even. It's really tough. That's good enough. Now, the first thing we're going to do is we are going to write down the constants that we know. Now, the important things that we are going to need is we're going to need these proportionality constants, the magnitude of them. We're also going to need our initial heights for each one. We're also going to need the cross-sectional area. You'll see why this is useful in a minute. Now, over here, I have my constants written down. I don't know if you can see that, but so let's just start by writing it down. You got to get started somehow, right? So we're going to start with our initial heights of each one. Now for the first tank, which I'll just give these numbers, I guess, might as well. Also, I just messed it up. Sleeve got in the way. I have so much marker on me. This one is going to be draining out just a little bit. Everyone has our first height is going to be 0.5 meters. I've recorded this so many times I've remembered all of them. Our second initial height is going to be 1 meter, and then our initial third height is going to be 2 meters. Now, like I said, the cross-sectional area is also very important for this because this is going to help us determine volume, our rate of change of volume, which we will see in a minute. So for these cross-sectional areas, it's the exact same value of the height, except it's meters squared as it's an area. So our cross-sectional area of 1 is equal to 0.5 meters squared. Cross-sectional area of number 2 is equal to 1 meter squared, and our cross-sectional area of number 3 is equal to 2 meters squared. Now, some other important constants is one of the big things we're going to be looking at. Real quick, let me just doodle some liquid in there. So I like to add some drops. Oh, also, in addition, we are going to have an initial surroundings height, which is going to be equal to 0 meters, meaning that none has drained out of the tanks yet. So, all right, let's get started with this. So when we look at this right here, there are 2 interconnecting pipes between these two, where the liquid is going to be moving back and forth at the bottom of these. Now, for ease of access, instead of talking about the type of material, the diameter, circumference of each pipe, the length of the pipe, what we're going to do is we are just going to have these alpha values right here. Which I'm going to use these in equations in a second. But again, these are just flow rate proportionality constants. And they're both equal to 0.1. I'm not 100% sure on the units, but for now we're just going to call it 0.1. Now what else do we have? Oh, so that's going to be like the flow rate right here. We're going to be using alpha for this, for our flow between 1 to 2 and our flow between 2 to 3. And as indicated by the arrows, which they're not very clear to see, it is pointing to the right for each of these. That is going to indicate the positive flow direction, which is going to become, I'll explain more why that's relevant in a couple minutes. Are we missing any other values? Oh, yes, of course. So as we see up here, we have a flow rate going into this, which we are going to call, we'll call it Qn. Now what we're going to use for this is we're going to use, not alpha, we are going to use a Kc value, which again is just a flow rate constant. flow rate proportionality constant. And what this is going to be equal to is our Kc value, which I will write that over here. Our Kc value is going to be 0.1 as well. Just like writing down all the constants, I'm going to put a picture of this when I do my code for later, just so I don't have to keep referring back and trying to memorize the equations and everything. So what this is going to be equal to is not K, is going to be equal to our, I forgot to write this down as well, our set point height, which I mentioned briefly in my introductory phrases, minus the height of the third one. So our set point, just draw a little arrow there, that is going to equal 4 meters. So what we want in our code when we look at our graph is we want to see a steady state that goes around 4 meters for the third tank right here. It has a set point, and this is going to determine our flow rate in. But what we want is we want our steady state when all of the lines have reached a constant value, no longer moving, hit a horizontal asymptote almost. What we want is the third tank to be at 4 meters. So let's continue. Now that we have most of the information we need, let's start talking about these flow rates right here, and we're going to use these alpha values right here. So I'm going to write all these in black since these are going to be the very important equations. So what we have is we have our flow rate between 1 and 2 is going to be equal to our alpha between 1 and 2. And what this is going to be, I'm going to add it now. I'll explain why after. This is going to be, we're going to have to add a sine function. And then this is going to be the absolute value of h1 minus h2 and the square root of that. Now that was given in the problem as it read. The magnitude of flow between two interconnected tanks is proportional to the square root of the difference between two of the tank's heights. So that's why we have this. The square root, we use the absolute value because it is a square root. And then what we're going to do is we're going to take the sign of this and just make it positive or negative because that's going to determine the flow, the direction of flow, if that's positive or negative. So let's say it's positive, it's going to move to the right, as you see with the arrows. And if it's negative, it's going to move to the left to tank 1. All right, and then we need the same thing for 2 to 3. We're going to use our alpha for 2 to 3. Same function, same things. We need the sine of the square root of h2 minus h3. So if h3 was bigger in magnitude, this would be a negative number. So what we're going to do is we're going to take that sign because it is going to be flowing into tank 2. If the height at tank 3 is higher than tank 2, then logically it's going to move back into tank 2, and that's going to be a negative value. So, and then that's a square root as well. So now we have these two equations, and what we're going to need to do is we're going to need to determine the rate of change of the volume, which is going to be using our cross-sectional areas and our heights in accordance with a differential equation using time. And what we're going to do is we are going to be using a differential equation solver. I believe it's called initial value problem solver in SciPy. And we're going to be doing that to determine the rate of change of volume. And then what we can do is we can divide out the cross-sectional area so that we're just left with height, and we can graph our height. So let's start doing it then. So what we're going to need is we are going to need our rate of change of volume. Now, for now, I'm going to erase these just to make room. Actually, I'll just spin it down, I guess. So I just don't want to go out of camera sleep. So let's start with our first equation. So again, I was talking about the volume. So what we're going to use the cross-sectional area of the first one, as well as the height with time, is going to equal the negative flow of Q1 to 2. Now, why is that? Because the only change in volume is going to be if this value right here is negative, because it has to be that H2 is bigger than H1, makes us a negative value, so we need to bring the negative down here to display that. Hopefully I explained that properly, or sufficiently. Now, what else are we going to have? We are going to have the second one. And it's going to be the same thing, except this one has a lot more factors. So what this is going to be equal to is we're going to need our flow rate from 1 to 2, positive, because if it's positive, it's going to be, if the height in 1 is higher, than the one in height 2. It's going to be flowing this way. It's going to be a positive sign, not a negative like before. And we're also going to have to add our QN value. Quick thing about the QN is it must be positive. We are not sucking anything out of this system. We are only putting liquid in when necessary. And also we're going to have to subtract, no, yes, no, yes. We're going to have to subtract the flow from 2 to 3. Yes, okay. Because again, we're going to subtract that because that is when liquid is flowing forward. It is going to be losing that amount of flow, that amount of liquid, causing the rate of change to diminish of the volume. All right, and then we're going to do the same thing for our third one and just use all the relevant factors. So derivative of third height with respect to time, and again, these two together make the volume, is going to equal positive Q 2 to 3, positive 2 to 3, and Q out. We will subtract Q out, which I actually don't have an equation for Q out. If I really do need it, let me know, Carlos. I assume it's just going to be whatever height leaves the system. But these are all of our relevant equations we're going to need, and this is going to give us. This is going to end up giving us these. Our whole goal is to get these rate of change of the volumes to figure out the heights, and what we're going to try to do again is we're trying to get the third tank in unison with the other two's flow in, flow out rates. We're trying to get this to have a desired height of 4 meters, that last tank. So thank you for watching. Let me know of any mistakes, and thank you for watching.